Hello, and let us look at the various topics which we are going to do in this lecture. First of all, we must know what a computer is. So we are going to look at the basics with the very basic components and very basic model of a computer. So we are going to do the basics of a computer. Then, as C is a programming language, we will be looking at what exactly programming means and what are the different types of programming languages and what are other programming languages related to C. So we are going to do this. Another term which is very popular in computer science is algorithms. So we are going to look at algorithms. And then there is a type of algorithm known as flowcharts, which is a pictorial representation of algorithm. So we are going to do flowcharts also. Okay, now first of all we need to know what a computer is. So beginning with a computer, so we have a computer. What do we give to the computer? We instruct the computer to perform some task and it gives output. So it gives some output and we give it instructions. But along with instructions tell the computer what to do. But a computer needs some extra information and what to operate upon. So that we give in the form of data. So as you can see that instruction and data form the input to the computer. Computer processes these instructions and data and produces some output. And this computer performs arithmetic and logical operations. Performs arithmetic and logical operation. And one of the most important thing one must know about a computer is that who developed the first computer. So it was first developed by a man named Charles Babbage. Let me write it. First developed by Charles Babbage. Let us put it this way. We have a keyboard, a mouse. Of course, we have the processor also. We also have a monitor. Monitor is a screen on which you view the contents of the output of the computer. Similar to a monitor is a printer which gives data from the computer. What you have more? Yes, we have a hard disk. And we also have a RAM inside a computer. So if you look at it carefully, the processor is the very important part of a computer. It is also known as CPU, Central Processing Unit. It is the most important part of the computer. Another part is the input and output devices. So these keyboard and mouse form the input devices. These give data to the computer. Input devices. Similar to input devices, those devices which take data from the computer, which display data from the computer, or which output the data from the processor are known as output devices. What remains is hard disks and RAM. So these store data. Some data you give through keyboard and mouse, but some of data which is very huge, which has a large chunk. So this data is stored in hard disk and then given to the processor. So you can give data and take data from a hard disk. You can write to the hard disk, you can read from the hard disk. Similar is the case with RAM. As you can see, hard disk and RAM are two different devices. So these are actually storage devices. But storage devices are primary. They are classified into primary and secondary storage devices. Take the example of hard disk. In the hard disk you store data, and after that if you switch off the power and again after some time switch on the hard disk, switch on the power, turn on the computer, the data in the hard disk is as it is. There is no change in that data. So this type of devices which are non-volatile, in which the data remains even if you switch off the power, are called as secondary devices, secondary storage devices. On contrary, if you take the example of RAM, the RAM is random access memory. It is a fast memory. The processor uses it. So the RAM, if you switch off the power, the data in the RAM is lost. So RAM is a primary storage devices. Why primary? Because mainly the processor uses RAM. Okay, let us now look at programming. What is programming? We have a lot of problems in this world. So we have problems. So many problems. But how do we solve problems? There is a simple way to solve problems. First we analyze that problem. Right? We analyze that problem. Then we do some designing and preparation of solutions. So we design and prepare a solution for that problem. Design and prepare solution. Right. After that, when the solution is ready, that we can solve this problem using this solution, what we do is we test that solution, whether it is working or not. Testing comes the third process. After testing, we write something about it, what we did, how we did it. So we write about it. This is a general process of solving problems. But this process is also applied in computer science. Any problem you have to solve using a computer, using programming, what you do is analyze the problem, you design and prepare the solution which are in the form of programs. Right? And after that you test it. The testing phase comes under that, and after that, after testing, you write about it. You write how you wrote that program, what was your strategy, and how to use that program, all other stuff. So this comes under documentation. So this is documentation. The programming is a four-step process: analyzing, designing and preparing the solution for problems, then testing it and writing about it. Now continuing with the programming part of our lecture, let us say we have a computer. You tell it to do work. You say do work. Then a computer does work. It does something. It follows your instructions. So it does something and says that work is done in the form of output. It shows you some output. Right? So what a computer does is it executes programs. It executes its programs. But what do you do when you say do work? When you say do work to the computer, you provide it nothing but programs. You provide it programs. And these programs are nothing but instructions. Instructions you tell the computer to follow to solve any problem, and it gives you the output. So in short, programming is nothing but the act of writing programs. Programming means writing programs. So this is a very simple step of writing programs, is called programming. Enough with programming. Now let us look at what computers understand. Computers understand only one language, that is binary. They don't understand English, they don't understand C, C++. They understand only binary language, which is nothing but 0 and 1, only 2 digits. Now a question naturally arises, why binary? As you know, computer is nothing but is made of electronic devices, right? Electronics means transistors. Everything inside the computer, the processor, is made up of millions of transistors. A lot of transistors are there. And transistors in electronics terminology are nothing but switches. Which perform only two things, on and off. Like on and off are very easy to represent in electronics. And on means 1, off means 0. So it's so simple. Now there arises a small problem here. We humans understand the decimal number system. So we have, let us say for example, a number 123. How do we recognize that it's number 123? There is a 3 in ones place, there is a 2 in tens place, and a 1 in hundreds place. So that is why we say that it's a decimal number system. Why? Because the places are the powers of 10. 10 raised to n, 10 raised to 0, 10 raised to 1, 10 raised to 2, and so on. So we recognize numbers in the powers of 10. On the other hand, we have the binary for the computer, binary system. It is nothing but 2 digits. Why decimal? Because we have 10 digits, 0 to 9. That is why we have powers of 10. Here it's different. We have powers of 2 raised to n. Let's say we have a number 0101. So we have the 1th power of 2, the 2th place, the 4th place, and the 8th place. So this is 2 raised to power 1, this is 2 raised to power 0, this is 2 raised to power 1, this is 2 raised to power 2, and this is 8 is 2 raised to power 3. So this way we have the binary. And if you want to know which number represents 0101 in binary, we have to convert it in decimal, and the process is very simple. This 0 is in 8's place, so 0 into 8, plus this one is in 4th place, so 1 into 4, plus 0 into 2, plus 1 into 1. So this is 0 plus this is 4 plus 0 plus 1. So what is this? Equals to 5. So this number is nothing but 5. 5 is represented like this in binary. Okay, this is all about numbers. How do we represent alphabets? You see alphabets on the screen. So how do we represent alphabets? It's so simple. Let me show you. Alphabets are represented as numbers. Let me write it. Represented as numbers. We have codes for alphabets. A has 65, B has 66, C has 67, and on and on and on. Similarly, for small a we have 97, small b has 98, small c has 99, and so on. So we have for capital and for small letters we have different codes because we represent them as different objects. Small a is different than the capital A, right? So these codes, every symbol is represented in this code. all the symbols you see on your keyboard, even the numbers, sometimes numbers are also represented as codes. So these codes are called as ASCII codes. ASCII, American Standard Code for Information Interchange. It would be better if I write it. American Standard Code for Information Interchange. Right. Numbers done, alphabets done. What about programming languages? How are they represented by the computer? So let's say we have a computer here. My drawing is not so good, so I'll assume that this is a computer. It only understands 0, 1, 0, 1, 1, 0. Only the binary language. It does not understand C++ or C or Java. It does not understand this. So how do we make a computer understand C, C++ or Java? We do nothing but let us say we have the language C. We take it, we convert it to 0, 1s and 0s and 1s, that is binary, and then give it to the computer. So this process of conversion is called compilation. This is called compilation. It is nothing but translation. You translate a language known as C into the binary language. So this is called compilation. Now there are a lot of tools available for this compilation. The first one is known as a compiler. Compiler is there. We also have something called as an interpreter. And the third one is not popular, is an assembler. So these things, these tools which are available, do nothing but conversion from languages like C, Java or C++ to machine languages, means zeros and ones, to the binary language, to the language which the computers understand. These convert the language which we understand to the language which computers understand. Right? So first of all, let us take a compiler. It detects all errors. Apart from converting the program, it detects all errors in that program. In the whole program, it detects errors in the whole program. And it translates the program in the whole. It does not translate it by part by part. Translates whole programs. Then we have the interpreter. It translates line by line. It translates line by line. It does not take the whole program and translate it and give to the computer. It translates it line by line, the first line, second line and third line. It also detects errors, but it can detect errors only in the current line being processed, right? It cannot detect errors in the whole program because it does not translate it as a whole. It translates it line by line. So it detects errors in the current line. And the assembler is for assembly language. It functions very similar to the compiler. It takes the whole program and translates it, but the program is built in assembly language, not high-level languages like C or C++. Okay, now let us look at programming languages. Programming languages. We use programming languages to write programs. We have three types of programming languages. One is machine or low level languages. Machine or low level language. Machine or low level language. Another is assembly or mid level language. Assembly or mid level language. And the third one is problem oriented or high level language. Problem oriented or high level language. So we have three types of programming languages: low level, mid level and high level. The low level language is, let me first partition these three different types of languages so that there is no confusion in between. Okay. Now the low level language or the machine language is the language which is understood by the machine. So it is obviously the binary language. And it is, as it is directly understood by the machine, by the processor, the computer understands only the low level language. It is directly executed. It does not need any conversion because it directly understands it. So it is directly executed. And as it is directly executed, it is very fast. If you write a program in low level languages, it is bound to be run very fast. But we are the people living in the decimal age, so it is difficult to write programs in the binary language. So it is difficult. Okay, now coming to assembly or middle level languages, which are a level up, a level higher than the low level languages. To remove the complexity of the low level languages, which are quite difficult to understand, these binary languages or these binary bits are grouped and given meaningful names. Meaningful names. Words, meaningful words like add, if you want to add two numbers, so add, move, moving from one memory to another memory space, and sub. There are a lot of instructions like these. We don't have to give them in binary. We have to give them in English, which have some meaning. It is easier than the language defined before. It is easier than the machine level language. Easier than machine level language. MLL, machine level languages. Another aspect of the assembly language is that it is machine dependent. There are a lot of processors and lot of computers available in the market. Everyone defines its own assembly language. Like we have Intel, we have AMD, we have the ARM architecture. So these processors have their own assembly languages. Okay, now let's move on to the problem-oriented or high-level languages. The high-level languages are English-like. We have English-like sentences. And as English is very easy language, we are very familiar to English. So the high-level language is very easy to understand. Very easy to understand, to implement, to write programs in. Because we understand English, right? High-level languages are machine independent. Machine independent. Why? Because of the feature called as compilation, which we looked before. Because these high-level languages are compiled, are translated to the low-level language, we can have a translator which translates one high-level language to the machine-level language of Intel processor. We can have another compiler or translator which translates the same high-level language to the to the low-level language of another processor, for example AMD. The concept is very similar. For example, you want to translate Hindi to English. What would you do? You would hire an English translator, right? If you want to translate the same Hindi language to Chinese, you hire a Chinese. So the concept is very similar. But the important thing here is that assembly level language or the high level language or the problem oriented language are compiled. Now one more thing remains here is that high level languages are English like. I said that before, but English has some rules, right? Rules for writing, rules for pronunciation, rules for making sentences, right? So these have rules for writing. And these rules for writing are known as syntax and semantics. Syntax deals with the positioning of words, and semantics deals with giving meanings to the sentences. That's all you need to remember at this point of time. Now the penultimate topic remains here is that of algorithms. We have a lot of problems in this world. We have lot of problems. Now we looked at solving the problem. We first analyze, then design the solution, then test it, then write about it. That is one case. But any problem, the real life problem, what is your first approach towards solving the problem? If the problem is very big, the easiest way to solve that problem is to break it. And solve it step by step. This makes the complexity of such a huge problem come down to small steps, and you can always solve step by step a huge problem one at a time, and then combine these steps to build a solution for that huge problem. So step by step solving is a proven method in real life, and also a proven method in computer science too. And this step by step solving of a problem, this step by step solution of a problem is nothing but algorithm. So let me repeat it again. An algorithm is nothing but a step-by-step solution for a problem. It is not a program, it is just a step-by-step solution of a problem. We do follow algorithms in our real life too. For example, let's take an example of making tea. There is an algorithm for making tea, right? First is warm a little water, right? For making tea you need water. The second step is you add sugar into that little water. The third step is after adding sugar you add tea. You add tea leaves. And the fourth step is after the sugar and the tea dissolves, you add milk. And the final step is nothing but you filter and serve. Right. This is a simple algorithm for making tea. We love tea, right? we now take a serious example, a mathematical example. Which number is greater? We have to do nothing. We have to take two numbers. We have to determine which is greater. A is greater or B is greater. Such a simple solution for this problem. So we have two numbers A and B. First of all, the first and the foremost thing you need to do is to take that input. You need to ask for two numbers. So you take input. You take input A and B. The second step you do is to check whether A is greater or B is greater. If A is greater than B, then tell that A is greater. So we print A is greater. If not, that is else it means that B is greater. Else print that B is greater. And then the final thing you do is to stop, right? You stop after checking and after printing all other stuff. You stop after that. Let us write the characteristics of algorithm. Characteristics of algorithms. The first characteristic is input. The second characteristic is output. Let me list the characteristics first, then I'll explain. The third characteristic, finiteness. The fourth characteristic is definiteness. And the final fifth characteristic is effectiveness. Now let us learn what these means, the characteristic of algorithm. The input is what you take input from the user or from some another source. So the input for an algorithm should be 0 or more. The algorithm may take or may not take any input, but it should provide at least one output. At least one. The output should be at least one. The algorithm should be finite. It should end. It should not continue. It should not continue for infinite time. Right? It should end. Definite means that all the statements you do in the algorithm should make some sense. They should not be confusing. The statements in an algorithm should not be confusing. The statements must not be confusing. The last characteristic is effectiveness. The algorithm should be effective. It should do some work. It should do some work. So these were the characteristics of algorithms. Now we move on to the final part of our lecture, which is flowcharts. Flowcharts are very simple. The previous part was algorithms. In algorithms, we wrote our steps. In flowcharts, we draw an algorithm. Flowchart is nothing but diagram of an algorithm. Let us take the same example, the mathematical example which we wrote the algorithm about. Which number is greater, A or B. Let us change colors now. Which is greater? So we have to first start. To do anything, we need to start, right? Then what we did is we took input A or B, A and B. We need the values of A and B, right? To check them, we need some values. So we took input A and B. So take input A and B. So we are drawing an algorithm right here. Then we checked whether A is greater than B or B is greater than A. Then we checked, is A greater than B? If A is greater than B, yes, A is greater than B, then we print A is greater. If our assumption that is A greater than B was wrong, the condition A is greater than B, is A is greater than B was wrong, that is false, then we print B is greater. If A is not greater than B, then it means that B is greater. And after that, we need to stop. But we are stopping after printing B is greater. But what about if the control goes here? If A is greater than B, if A is greater indeed, then it goes here, prints A is greater. Then we need to stop after this also. So we connect it here. So this is nothing but a flowchart. And a flowchart always gives the flow of process. That's why it is called flowchart. It gives the flow, where the control goes, which statement is executed, if there is some condition, it shows everything. So this is a flowchart. Now a flowchart has to be drawn. It is a graphical representation of an algorithm. And as it is a graphical representation, there are some graphics involved in it. There are symbols, like this is a symbol, this is a parallelogram, this is a diamond, this is an arrow. So there are symbols involved in a flowchart. So we now look at the various symbols that are involved in a flowchart. What are the symbols involved in a flowchart? So first of all, we had a start or stop symbol, right? So it is represented as oval. Start or stop is represented as oval. When an algorithm starts, when an algorithm ends, that is an oval. If you have some input or some output, so that is represented as a parallelogram. Input or output by a parallelogram. And then if you have some process, you represent it as a rectangle. Another symbol involved is a diamond. We used the diamond in the previous flowchart. To check decisions is a diamond. Diamond. Another graphic involved is a hexagon for loops. For now, remember that hexagon is used to represent loops. Loops is nothing but a part of a program where some statements are executed again and again. That are called loops. We'll study what are loops in later lectures. But for now, remember that loops are represented using a hexagon. And if you run out of space, sometime it happens that a flowchart is so big that a page is not enough to accommodate it. So if you run out of space, no problem. You can connect a flowchart. So you draw some flowchart at some part of page, and in the next page connect it using a circle. Connector using a circle. And we saw that a flowchart gives the flow of process, and that flow of process was represented by arrows. And if you have some predefined process, we'll learn what a predefined process is. But for now, a predefined process is anything which is already defined in the language. So this predefined process is represented by this structure. I don't know what this structure is, but this structure represents predefined process. So these are the symbols of a flowchart. Now flowcharts have advantages. The biggest advantage is it is programming language independent. It is programming language independent. This means that you can translate a flowchart in any programming language you want. It is not dependent on any programming language. If you build a flowchart, you can implement that flowchart in C. If you want, you can implement the same flowchart in C++. There is no binding between any language and a flowchart. And the biggest advantage of a flowchart is that it is very easy to understand and to implement. Because pictures make more sense than words, and it's a proven fact, right? So it is easy to understand and implement. So that's all we have in this lecture. We are done with today's lecture. If you have any queries, you can email me. Let me write my email address here. gaurav.bhorkar@gmail.com. Alright. Thank you for listening.